Today guys, I'm General Canarias and I'm here to discuss about the vector operator del and the divergence theorem. If we remind ourselves again that divergence is an operation on a vector yielding a scalar result, just as the dot product of two vectors gives a scalar result, it seems possible that we can find something which may be dotted formally with D to yield a scalar equation of this. Obviously, this cannot be accomplished by using a dot product. The process must be a dot operation. With this in mind, we define the del operator as a vector operator of this. Similar scalar operators appear in several methods of solving differential equations, which we often let D replaced by its derivative, D squared replaced by its second derivative, and so forth. We agreed on defining del that it shall be treated in every way as an ordinary vector, with the one important exception that partial derivatives result instead of products of scalars. Consider del D signifying this equation. We first consider the dot products of the unit vectors, discarding the 6 0 terms and having left this. Where the parentheses are now removed by operating and differentiating, this is recognized as the divergence of D, so that we have use that divergent of D is much more prevalent than that of divergent D. Although both usage have their advantages, writing divergence.D allows us to obtain simply and quickly the correct partial derivatives, but only in Cartesian coordinates. As we shall see below, on the other hand, divergent D is an excellent reminder of the physical interpretation of divergence. We shall use the operator notation del D from now on to indicate the divergence operator. The vector operator del is used not only in divergence, but will appear in several other very important operations later. One of these, divergence U, where U is any scalar field and leads to the del operator does not have a specific form in other coordinate systems. If we are considering D in cylindrical coordinates, then del D still indicates the divergence of D, or where these expressions have been taken from section 3.5, we have no form for del itself to help us obtain this sum of partial derivatives. This means that delta U, as yet unnamed but easily written above in Cartesian coordinates, cannot be expressed by us at this time in cylindrical coordinates. Such an expressions will be obtained when del U is defined in chapter 4. We shall close our discussion of divergence by presenting a theorem which will needed several times in later chapters, the divergence theorem. These theorems apply to any vector field for which the appropriate partial derivatives exist, although it is easiest for us to develop it for the electric flux density. We have actually obtained it already and now have little more to do than point it out and name it, from starting from Gauss' law and letting Q is equals to the integral of rho v dv, then replacing rho v by its equal delta dot D. We will have the closed integral of dds is equals to Q is equals to the integral of rho v dv is equals to the integral of del dot D dv. The first and last expressions constitute the divergence theorem. The closed integral of dds is equals to the integral of v dot D dv. Again, we emphasize that the divergence theorem is true for any vector field, although we have obtained it specifically for electric flux density, and we shall have occasion later to apply it to several different fields. Its benefit derived from the fact that it relates a triple integration throughout some volume to a double integration over the surface of that volume. For example, it is much easier to look for leaks in a bottle full of some agitated liquid by an inspection of the surface than calculating the velocity at every internal point. Okay, thank you guys for watching.